Good morning. My name is Marie Rienzo, and I want to welcome you to the NIH Office of Disease Prevention's Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions to promote the use of the best available methods and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar by clicking on the question mark in the WebEx toolbar. Please direct your questions to all panelists. We will open the floor to questions that have been submitted via WebEx at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in approximately 1 week. You will receive an email when they are available. Lastly, we would appreciate your feedback about today's webinar. Upon closing the WebEx meeting, you will be prompted to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, Marie. Today's speaker is Dr. Stuart Baker, who is a mathematical statistician at the National Cancer Institute. Dr. Baker is well known for his work on the method of latent class instrumental variables, which he helped develop more than 20 years ago. His research also includes work on many aspects of prognostic markers, including benefit functions for evaluating predictive markers, identifying biologically relevant models in time series microarray data, and a biomarker pipeline to evaluate markers for the early detection of cancer. Dr. Baker was the first recipient of the Distinguished Alumni Award from the Department of Biostatistics at the Harvard School of Public Health. He is also a fellow in the American Statistical Association. It is my pleasure to welcome Dr. Baker.
Thank you. This is an important topic for anyone interested in prevention studies or health promotion studies. In the next 35 minutes or so, you're going to learn two useful techniques. The first is how to analyze randomized trials with all or none compliance. And the second is how to implement and analyze the paired availability design for historical controls. No complicated math here, just simple formulas with an emphasis on concepts, assumptions, and interpretation. It's helpful to explain the terminology in the title. By causal inference, I mean the potential outcomes viewpoint, which was discussed by Neyman in the 1923 thesis, but developed extensively by Don Rubin since 1974. And it asks the questions, what is the outcome if you went back in time and received a different treatment? Now, obviously, you cannot go back in time. So the way you make inference is through assumptions and indirect methods. And one indirect method is the instrumental variable. So an instrumental variable Z affects outcome Y only through treatment received T. So you have these diagrams with Z, the instrumental variable, with an arrow to treatment, with an arrow to the outcome Y. And importantly, there's no arrow that goes from Z to Y that's outside of T. And the quintessential example of the instrumental variable would be Z being the randomization group. And for the paired availability design, I'm going to talk about Z being time period if assumptions hold. Very simple outline. First, I'll talk about randomized trials with all or none compliance. Then I'll discuss the paired availability design. So randomized trial with all or none compliance. So persons are randomized either to a control group who are offered or assigned some treatment T0. So you can think of treatment T0 as a standard treatment, or it could just be no treatment in many prevention studies. Or they could be randomized to the experimental group where they're offered or assigned new treatment T1. And in each group, immediately after randomization, some persons receive T0 and some receive T1. And it's immediately after randomization, that's why it's called all or none compliance. And the goal is to estimate the effect of the receipt of treatment T1 versus T0, as opposed to an intent to treat analysis. So why are we interested in estimating the effect of treatment received instead of a treatment assigned? Well, obviously for patients making decisions, they want to know the effect of treatment received. In cost effectiveness analysis, you're comparing cost of treatment received and so it needs to be compared with the benefit of treatment received. In non-inferiority studies, you want to see if the treatment effects are the same the effects are the same for two different treatments, and you have a tolerance, and so you want the tolerance to be based on the effect of treatment received. And in the meta-analysis of randomized trials, there's a contribution from each trial. You want it to be the effect of treatment received, so you weight each trial appropriately rather than the effect of treatment assigned, which could inappropriately weight the trial by how many people are choosing to receive the treatment. So to estimate the effect of treatment received with all or non-compliance, I'm going to discuss the method of latent class instrumental variables. So this method has been around for a long time, and there's been like no standard name for the method. Sometimes very long, unwieldy name. Sometimes no name. The early work had no name for it, or sometimes it was called modern instrumental variables. So in this review article, I decided to call it latent class instrumental variables. And there are many independent developments in the field. The early work was on one-sided all or non-compliance, which is all or non-compliance only in the experimental group. And when I was a graduate student in 1983 at Harvard in the biostatistics department, I wrote a technical report discussing this one-sided all or non-compliance with maximum likelihood estimation. Then there have been papers by Bloom in economics, and then papers in statistics and epidemiology. And the more general situation is two-sided all or non-compliance. And 1994 was the big year for this. And there was papers by Imbens and Angrist in Econometrica. And then a paper I wrote with Baker and Lindeman in Statistics in Medicine, which discussed the paired availability design that I'll discuss later. And probably the most well-known is this paper by Angrist, Imbens, and Rubin in 1996. And recently, these three papers were called seminal by Swanson et al. In a JASA review article. So the latent class instrumental variables has four parts. So the first part are the latent classes based on treatment received if randomized to each group. And these are also called principal strata. So here's a table, and you have group assigned T0, group assigned T1, and the treatment received. And an always taker, these names, always taker, never taker, complier, and defier, come from Angrist, Imbens, and Rubin. So an always taker is someone who would receive the new treatment T1 regardless of the group assignment. A never taker is someone who would never receive T1, receive T0 regardless of the group assignment. A complier is someone who complies with the group assigned, so receives T0 when assigned T0, receives T1 when assigned T1, and a defier does the opposite, receives T1 when assigned T0, T0 when assigned T1. And these are all baseline variables. Now, to make progress, it's necessary to have some assumptions, and they have these very technical sounding names. The one assumption is monotonicity, and that just says we're going to assume there are no defiers. So this is a rationality assumption, and nobody's going to be irrational and always do the opposite, receive the opposite of treatment that's assigned. The second assumption is called the exclusion restriction, and this is a consequence of having an instrumental variable, a randomization group. And it says that for always takers and never takers, randomization group does not affect outcome because they're receiving the same treatment, T1, T1, regardless of the group, T0, T0 for never takers. Now, with these latent classes and these two assumptions, you can estimate the causal effect in compliers. and that is the estimated difference in potential outcomes, so outcome if received T1 instead of T0, in compliers. And this is simply, it's all very complicated, but it turns out it's a very simple statistic. It's the difference in outcomes between the two groups, which is the intent to treat estimate, divided by the difference in fraction receiving T1 between the groups. And this has two names in the literature. In the economics literature, it's often called the local average treatment effect, LATE. And in the biostat literature, it's often called the complier average causal effect, CACE. And now, in the next set of slides, I'm going to explain why, how this estimate comes about with these assumptions and latent classes. So here's the hypothetical example. We have two groups, randomization groups, assigned T0 and assigned T1. And to keep the example simple, I'm going to assume the same number in each group, 40,000. You don't have to have the same number in each group, but it makes the example simpler. And so those assigned T0, some receive T0, some receive T1, and similarly for T1. And now we have the various latent classes that make up these different assignments. So among persons assigned T0 who receive T0 is a mixture of two kinds of latent classes. So some of these people are never takers because they always receive T0. And some are compliers because they're complying with receiving T0. And you have a mixture. You don't know how many in each part of the mixture, and that's why we're going to need the assumptions. And then for those assigned T0 and receive T1, you have a mixture of always takers because they're always getting T1, or they could be defiers. They receive the opposite of what they're assigned, and so forth. So let's clear this, and now we're going to show how we can fill in this whole table, how everything is identifiable based on the assumptions. So we'll start off with the monotonicity assumption that there are no defiers. So that means everyone in this group assigned T0 and T1 are always takers. So we can take the 20,000 and then we assume the outcome's death and put it here. And similarly for the never takers. And we can just fill it in like this. Then we get to the next assumption, the exclusion restriction. And that says the treatment effect does not depend on group. And we'll first look at always takers. So we can take the always takers here and copy from the group assigned T0 and just copy it down here under the assumption. And then to get the number of compliers, you just subtract. We have 30,000 minus 20,000 is 10,000, and 120 minus 80 is 40. And then we do the same, the exclusion restriction for never takers. So we take the never takers here. It's the same. The treatment effect doesn't depend on outcome. So the same here, and we just copy right here because we have the same number in each randomization group. And then we're going to subtract to get the number who are compliers. So you see we filled in the entire table based on these assumptions. Okay, so then we have, with some algebra, turns out with this filled in table, you can get this estimate that's the difference in outcome between the groups over the difference in fraction receiving T1 between groups. And let me give you some intuition on this. So in the numerator, there's contributions from never takers, always takers, and compliers. But the contribution from always takers and never takers are the same for the two groups, so they're just going to cancel. So what you're left in the numerator is, after they cancel, is the joint probability of being a complier and the outcome for the complier. Then the denominator turns out to be just the probability of being a complier. So it's the difference in fraction receiving T1 between the groups. So the fraction receiving T1 who are assigned T1 is a combination of always takers and compliers. The fraction who receive T1 who are assigned T0 are just always takers. So if you take this fraction and subtract this fraction, you get the fraction who are compliers. So that's the intuition behind this statistic. Okay, so let me summarize. For latent class instrumental variables, you have 4 latent classes: always taker, never taker, complier, defier. You have the monotonicity assumption and no defiers. You have the exclusion restriction, same treatment effect per group for never takers and always takers. And then you get your estimated causal effect in compliance, which is your intent to treat estimate divided by the difference in fraction receiving T1 between the groups. And you'll often see this called local average treatment effect or complier average causal effect. Okay, let's go through some examples now. The first example, the effect of breast cancer screening on breast cancer mortality. And women were assigned either control group of no screening. This was in the 1960s, so there was no screening available unless you got an invitation, or the screening invitation. And 65% of the women invited for screening agreed to get screened. And so the intent to treat estimate is just this difference in breast cancer mortality rates in the 2 groups. And the causal effect in compliers, you take the intent to treat estimate and divide by this 65% to get this inflated estimate. And this is one-sided all or none compliance. Okay, here's another example of one-sided all or none compliance. This is the effect of vitamin A supplement on mortality in preschool children. So the experimental group were assigned vitamin A and the control group received nothing. And there were some distribution problems, so only 80% of those assigned vitamin A received vitamin A. So the estimated causal effect in compliers is just the intent to treat estimate divided by this 80%, 0.80. Okay, third example, another one-sided all or none compliance. This is the effect of ankle rehabilitation exercise on re-injury. So the persons were either randomized to no rehabilitation or invited for rehabilitation, which involved exercise. And 61% received some form of exercise. Again, we take our intent to treat estimate, divide by this 61% to get our estimated causal effect in compliers. Okay, here's another example, effect of job training seminar in unemployed persons on subsequent depression. Now, this is, again, one-sided all or non-compliance, but here, unlike the other examples, the outcome is a continuous measure. It doesn't have to be a binary outcome. This is the mean depression score. So they're randomized either to a control group or a seminar invitation, and 56% showed up for the seminar, and the estimated causal effect in compliers is the intent to treat estimate divided by this 56%. Okay, example 5. Now we have two-sided all or none compliance. This is the effect of stopping maternal smoking on birth weight. So in the control group, 20% stopped smoking. In the experimental group, 43% stopped smoking. The causal effect in compliers is the intent to treat estimate divided by the difference in the fraction who stopped smoking. Example 6, another two-sided all or none compliance, effect of flu vaccine on hospitalization. And this is a little different because instead of encouraging participants, the encouragement comes to the physician. And they were reminded to give the vaccine. So in the control group, 26% of the participants received the vaccine. The experimental group, 43%. And the causal effect in compliers is just the intent to treat estimate divided by this difference. Okay, let's talk about confidence intervals now. So I'm talking about the risk difference confidence interval, but what I have to say applies directly to a confidence interval for a continuous outcome. So for an intent to treat, the estimated effect is just the difference in the fraction receiving outcome 1, P1 minus P0. Then you have the usual binomial standard error, and you have the usual 95% confidence interval. Now for the causal effect in compliers, Remember, we take the intent to treat estimate and divide by the difference in the fraction receiving treatment T1. That's F1 minus F0. For the standard error in compliers, it's approximately the intent to treat standard error divided by the difference in the fraction receiving treatment. And that's assuming this fraction is known. And in prevention studies, that's usually a pretty good assumption because they're usually very large. And so there's very little variability. And then you get your usual 95% confidence interval. So an important point is that this method is helping you with bias, but it doesn't help any with statistical significance. Because if you take the estimate from intent to treat and divide by the standard error for intent to treat, it's approximately the same as the estimate of the causal effect in compliers by the standard error in that estimate. So statistical significance isn't changed using this technique. It's just that your estimate changes to avoid bias. Okay, I want to go through 3 subtle points. So the first one has to do with the definition of the treatment. So as I said, the usual scenario, T0 is a standard treatment, T1 is new treatment. We have all or none compliance, and the exclusion restriction requires T0 and T1 to start at randomization. And you often get in the situation, what if some persons receiving T1 do not fully comply? And without making lots of restrictive assumptions that are probably very questionable, the thing to do is to reinterpret. And what you do is you would reinterpret T1 as starting a new treatment. And you're estimating the causal effect of starting the new treatment. And this is still useful because it's more informative than estimating the effect of assignment to the new treatment. Okay, second subtle point. If extra data are available, you can check assumptions for risk difference. Okay, so let me just go through the minimal data that you need to estimate the risk difference. You need the number of persons assigned to each group who receive each type of treatment, in this column here. And then you only need the number with the outcome in each randomization group. Now sometimes you have extra data on the number with the outcome who receive each treatment when they're assigned to each treatment. So in that case, you can compute 2 additional statistics, which are the estimated probability outcome is 1 given your complier in each group. And you have this more complicated formula here. But the important point is that these are probabilities. They have to be greater than or equal to 0. So you do this calculation. If they're greater than or equal to 0, you're fine. Everything goes through. If they're not greater than or equal to 0, you either have to do a different type of estimate, or more likely, the exclusion restriction doesn't hold, and you have to think about it very, very deeply. Now, interesting aside is you can compute relative risk, just as this ratio Q1 to Q0. And when you do relative risk, you need more data than with risk difference. And this can be a problem, and I saw this once with the meta-analysis. So the investigators did a meta-analysis, and they decided to use relative risk instead of risk difference. And many of the studies didn't have this extra data here. They only had the minimal data, and they had to discard those studies. And in meta-analysis, you don't want to discard any studies unless you have a really good reason. So that's a good reason to use risk difference with meta-analysis, that you often can incorporate more studies. Okay, the third subtle point is generalizability of the estimated causal effect in compliers. So there's something I call complier generalizability. So that says that you assume that the estimated causal effect in compliers is the estimated causal effect in everyone in the randomization group, like never takers and always takers, if they receive T1 instead of T0. And you can investigate this to some extent when you have a meta-analysis with multiple trials using what I call the causal generalizability plot. And I'll show you one very shortly. The name I came up with just for this talk. The second type of generalizability, which you have in all randomized trials, is generalizing the effect of treatment from the participants in the randomized trial to the population. So it's something that should always be kept in mind. Okay, so I mentioned meta-analysis, and let me go through this more formally. So suppose you have trial I, and let's let D complier I be the estimated causal effect in compliers in trial I, and we have a variance, estimated variance, and this is based on those formulas I showed you before. And you could do a fixed effect of meta-analysis or random effects. I'm just showing fixed effects here because it's simpler to show. And the estimated effect in the meta-analysis is the weighted average of the causal effects for each trial. We have weights, and the weights are inversely proportional to the variance in the compliers. And then you can get a standard error and then an overall confidence interval. Okay, so let me go to example 7, meta-analysis of randomized trials. And this is an example that I'll carry through with the paired availability design. This is the effect of labor epidural analgesia on the probability of C-section, which has been a controversial topic for some time. So one caveat with the randomized trials is this is not all or none compliance, because there were crossovers, and ideally for all or none compliance you want the crossover to occur at randomization, but some of them occurred after randomization. However, we thought the exclusion restriction approximately holds because there was paper showing that the timing of the epidural analgesia does not affect the probability of C-section. So here's the causal generalizability plot for the effect of epidural analgesia on the probability of C-section. So the horizontal axis is the estimated fraction who are compliers. This is the estimated by the difference in the fraction receiving epidural analgesia in each randomization group. And then the vertical axis is the estimated causal effect in compliers. This was our estimate from the latent class instrumental variables. And there were 21 trials, which I've listed here. And the points, the size of the points is proportional to the sample size. And you see this spans a large range. This one here, everyone's a complier. It's complete, there was no crossovers and a very small number of compliers here. And one important aspect that you see right away, there's no trend. So you'd be concerned about generalizability if you saw some trend here going up, say, in the fraction, in the estimated causal effect based on the fraction who are compliers. So given there's no trend, you did a random effects meta-analysis, and that showed a small effect. This was with a borderline statistical significance. Okay, so we're finished part of the talk on randomized trials, and now we're going to go to observational studies, the paired availability design. So this is work I did with Baker and Lindeman in proposing this design in 1994. And there are two time periods. You have a time period 0 when some treatment T1 is less available, and then a time period after that, T1, where treatment T1 is more available. And in each time period, a person could receive either treatment T0 or T1. And it's called paired availability design for the following reasons. It's pairs because you have pairs of time periods. And this is, as I'll explain, this is in multiple medical centers. It's availability because the availability is changing over time from time period 0 to time period 1. And it's a design because investigators can choose medical centers where they will increase T1 availability. And I'll discuss how they make these choices a little later. So when would you use the paired availability design? Obviously, you always want to do randomization if possible, but sometimes it's not possible, such as if you're randomizing someone to surgery or to a drug, you couldn't blind them, you're hard to enroll persons. You also would use the paired availability design when you can't use your standard observational study like with propensity scores because you're concerned about bias from unmeasured confounders or maybe there's a lot of missing data on covariates. And then finally, the paired availability design needs to be feasible. And as I'll discuss, an important aspect is you want a short-term endpoint to minimize systematic biases over time. And you want multiple medical centers to minimize chance biases over time. Okay, so let's discuss latent class instrumental variables with the paired availability design. So we have a thought experiment. We think of what treatment would a person receive if he or she would arrive, everything else being the same, in time period 0 when T1 is less available, or time period 1 when T1 is more available. And when I say all else being the same, one aspect would be if they arrive in the morning, time period 0, then in the thought experiment, they would arrive in the morning, time period 1. And we have 4 latent classes, and this is more receiving treatment than taking treatment. So I came up with these 4 names to parallel the names that I discussed before with randomized trials. So we have always receivers who would always receive T1, never receivers who would never receive T1, always receive the standard treatment T0, consistent receivers, consistent with availability, they receive T0 when T1 is less available and T1 when more available, and then inconsistent receivers. And I'll be going through an example with the epidural analgesia again. And so T0 is no epidural analgesia, T1 is epidural analgesia. Again, these are baseline variables. So there are 4 sets of assumptions so that the time period can be treated like randomization group in the sense of being an instrumental variable. So the first assumption is stable population. So that says the composition of the population related to outcome doesn't change over time. So it would be violated if someone, there was self-selection, so persons were actively seeking out the new treatment, going to a particular medical center just to seek out the new treatment. So you could strengthen the design by having geographically isolated medical centers. So going back to our epidural example, a woman who's in labor is unlikely to deliver at a hospital that's very far away just because it has epidural analgesia. She'd more likely go to the closer geographically isolated medical center. Another way to strengthen the design is to have something like an Army Medical Center where there's a restriction of the population who can be served by the medical center. The second assumption is stable ancillary care. So that means management of the patient unrelated to treatment doesn't change over time. So you want to have the same staff, so an epidural analgesia, the same obstetricians. You want to have a strict protocol. And then above all, you want to have a short-term study. The longer it is, the more likely there could be changes in ancillary care over time. Now, there are 2 other assumptions that don't relate to the epidural analgesia example, but could apply in other situations. We have the stable disease assumption that the natural history of disease doesn't change over time. So if you had if you were studying some virus and there's a new strain over time, that could violate this assumption. And then you have the stable evaluation assumption. So that says the method to evaluate outcome doesn't change over time. So if the outcome is stage of cancer and there's a new testing procedure, that would violate the assumption. Then we also have 2 assumptions to estimate causal effect in the consistent receivers. So the first assumption is stable treatment effect, which is like exclusion restriction. It implies exclusion restriction. And it says that the effect of treatment on outcome is unchanged between the two time periods. And there are two ways it could be violated. One is if you have an increase in treatment T1 availability, means that T1 arises sooner in the time course of the disease. So we weren't concerned about this with the epidural analgesia example because of that paper that showed that the timing of it did not affect the rate of C-section. It could also be violated if T1 changes due to more experience. So for example, T1 is surgery, and the more procedures a surgeon does, the better the outcome. That would violate this assumption. And if you're really concerned about it, you would have little availability of T1 in time period 0. Okay, the second of the set of assumptions is stable preference. And this is related to monotonicity, and as I will explain, something called randomicity, which is the name I gave just because you'll see, but to make it sound like monotonicity. So it says the preference for treatment doesn't change over time. And this would be violated if you have a publicized harmful side effect. And a way to strengthen the design is no advertising of any new treatment. So let me explain the stable preference assumption in a little more detail with the monotonicity and then its randomicity. So the availability of T1 at time period 1, when it's made more available, could either be fixed or random. The example of fixed, and I'm talking about our epidural example, is if there's an epidural service, say from 9 to 11 a.m. And so in our thought experiment, the person is coming in at the same time of day in the first time period and the second time period. And so this fixed availability would mean that there are no inconsistent receivers. They wouldn't get the, there's no one who would not get epidural when it's available and vice versa. Now there's also, you can also have random availability. So, you have an anesthesiologist to administer the epidural, but the anesthesiologist comes in at different times. And it's sort of a random schedule. Well, in that case, there's really no difference between a consistent and inconsistent receiver. It's just by chance, person's consistent or inconsistent depending on when the anesthesiologist comes in. And so that's what I call randomicity. And it doesn't matter if it's monotonicity or randomicity. The estimated causal effect in consistent receivers is the same type of estimate. You have a difference in outcome between time periods divided by the difference in the fraction receiving T1 between the time periods. So very analogous to what we had with the randomized trials. So now we have a causal generalizability plot for the paired availability design, which by definition has multiple medical centers. So here we have 10 medical centers. The horizontal axis is the fraction who are consistent receivers, and the vertical axis is the estimated causal effect in consistent receivers. This is the estimated rate of cesarean section in consistent receivers, and this is the difference in the fraction who receive epidural analgesia in each medical center. And so it goes from 0 to 1, but you see it's all clustered more together than with the randomized trials. And again, you see no trend, so you're not worried about problems with generalizability. And the meta-analysis estimate, this was the random effects meta-analysis, showed there's no statistical significance, and the confidence intervals narrow. So let me summarize about the effect of epidural analgesia on the probability of C-section. So in the earlier part of the talk, I discussed the meta-analysis of randomized trials for the effect of epidural analgesia on the probability of C-section using latent class instrumental variables to adjust for the crossovers. And the risk difference estimate was very small with a borderline significant 95% confidence interval. Then some investigators have done multivariate analysis of concurrent observational data. This was with propensity scores. And there were two large studies with lots and lots of covariates. It's just showing just a fraction of all the covariates they used. And they estimated very large relative risks with large lower bounds on the 95% confidence interval. And we were concerned that there was an unmeasured confounder. And the unmeasured confounder we were concerned about was pain in labor. Because a woman who's in high pain in labor is obviously more likely to get epidural analgesia. But high pain in labor is also makes the woman more at risk for cesarean section. And we think this could have explained the large relative risks in these studies. And then we have the paired availability design. And that's estimating a very small risk difference and a non-significant 95% confidence interval. And we were glad that it was reassured, I should say, that it was similar, qualitatively similar to the risk difference estimate with the meta-analysis of randomized trials. Okay, so in conclusion, so first I discussed randomized trials with all or none compliance, and the estimated causal effect in compliers is the difference in the outcome between the two groups, this is the intent to treat estimate, divided by the difference in the fraction receiving the treatment T1 between the groups, the experimental treatment. And it's based on reasonable assumptions. Remember, monotonicity, the rationality assumption, the exclusion restriction, which likely holds with all or non-compliance, and this latent class instrumental variable framework. And then we have the paired availability design, and that estimates the causal effect in consistent receivers. Again, a very simple estimate, the difference in the outcome between time periods over the difference in the fraction receiving T1 between time periods. Again, reasonable assumptions. And the key design considerations. First of all, we want multiple medical centers to average out chance variations over time. Second, it's very important to have a short-term endpoint because you don't want any systematic bias over time, and this will likely minimize the systematic bias over time. And then also, you want to have the staff and the protocol to be the same over time. Like when we were doing the study and looking up all the different studies with the epidural analgesia example, some of them actually wrote the staff was the same, the protocol was the same over time. Okay, well, I thank you all for your attention, and I'd be very glad to answer any questions.
Thank you, Dr. Baker. Very interesting presentation. We've got a number of questions for you. Some of them are simple, basic, and others a little bit more nuanced. We'll start with some of the simpler questions. So if you've got a randomized trial and everybody completes the treatment as assigned, so that there's 100% compliance, is the intent to treat estimate going to be the same as the causal effect in compliers?
Yes, because everybody's a complier.
So no difference between the two estimates and no difference between the p-values?
Yeah.
Okay. All right. Then this gets at the heart of the purpose of this approach. Why should we pay more attention to the causal effect in compliers than to the intention to treat effect? It doesn't change the p-value, you told us. It does change the estimate itself. And why should we pay more attention to one than the other?
Well, yeah, you're correct. It doesn't change the p-value, but it has to do with the bias in the estimate. And I would argue that the causal effect in compliers is more likely representative of the effect than the intent to treat estimate, because the intent to treat estimate is diluted by the never takers and the always takers. And it's very important. This goes back to one of my earlier slides. But when you would use it, maybe I can go back to it and I'll show you again. It's if you're doing cost-effectiveness analysis, you're going to get the wrong answer if you got the cost of the treatment received and then you have the intent to treat estimate, because it's diluted. And for a non-inferiority study, you're going to get an incorrect analysis. And then for a meta-analysis, you have a couple trials. Say there's many people. In some trials, there's a lot of compliance. In some trials, there's little compliance, and it's going to incorrectly weight your trials with a large compliance. So in all these situations, the bias is the key, and particularly with the meta-analysis, and also, obviously, the cost-effective analysis in the non-inferiority study.
Thank you. In the randomized trial application, there were a series of assumptions, and one of our listeners is asking, what's the impact on the results if one or more of those assumptions is violated, and does the impact vary depending on which one is violated and on the magnitude of the violation? There's a lot packed into that question, but I'll leave it in your hands.
Yeah, well, that's very hard to, when you say it's violated and you want to know the impact, you have to know exactly how it's violated. So I can't give a general answer to that, unfortunately. If, as I said, in the examples I gave, the exclusion restriction, we were concerned about that with the randomized trial with the epidural and analgesia. So we had to, and we had crossovers, so it didn't occur immediately after randomization. So we had to look in the literature to see that the crossovers probably don't affect the exclusion restriction. So my best advice is try to see if these assumptions hold. If they don't hold, there's so many ways it could be violated. It's hard to come up with a general statement, any general recommendation.
Yeah, I guess part of my answer to the question might be pay attention to the material on some of your slides where you offered ways to strengthen the design to protect the assumption.
Right, that's more for the paired availability design, and that was more the assumption related to using time periods like randomization groups. They didn't want any systematic bias over time, which is a big concern.
We have another question using some acronyms that I may not entirely understand, so I hope that you will. Can this approach be used to estimate the ATE instead of the LATE, since policymakers and researchers are mostly interested in the ATE?
Okay, well, I think by ATE, they mean the intent to treat estimate. And I'm not so sure that policymakers are always interested in the ATE, because that makes the assumption that the fraction of people who receive, who comply, is going to be the same in your trial as in your study. I mean, as in the general population, which is probably not true. And then again, for the slide I have showing up here, I think policymakers are interested in cost-effectiveness analysis, and they're interested in meta-analysis. And so you wouldn't be interested in the ATE in either of those cases when you have all or none compliance.
So you have focused on the all or none compliance case. And what if we have something that's different from all or none? What would that look like, and is this method still applicable?
Okay, well, I have some supplementary slides because I thought this might be a question. And I'll show you why, if you have partial compliance, you have a problem. And so imagine you have this is like the simplest example I could think of where you have partial compliance instead of all or none compliance. So you have T0 as a placebo. T1, you get new pills, and then you stop receiving the pills. And T2, you receive the new pills continuously. So it's not all or none, there's partial compliance. So let's see what would happen if you tried to apply this method, these assumptions with partial compliance. So now we have two kinds of always, you have a group assigned T0 and a group assigned T2, because you're assuming that everybody's going to comply completely, but some are going to be receive T1. So you have an always taker who always receives T2, an always taker who always receives T1, and then a never taker who never receives, either always receives T0. And then you have three kinds of compliers. You already see this is getting very complicated. You have compliers who receive T0 and then T1, T0 and then T2, and then T1 and T2. And then similarly, there's three kinds of defiers. So now let's make our usual assumptions that are reasonable. Remember, no defiers, so that knocks out these last three, so that makes things simpler. And then we have the exclusion restriction for always taker, the two kinds of always takers and the never takers. So we want to see if it's identifiable. And the way to see it's identifiable is count parameters versus independent counts. If you have more parameters than independent counts, it's not identifiable without having more assumptions. So let's count parameters. We have 14 parameters total because we have 5 independent latent class probabilities. So here are like 6 categories after we drop defiers, but to make them independent, we drop 1, so that's 5. And then we have 9 outcome probabilities. So for each always taker, you have 1 outcome probability, and then 1 for the never taker. And then compliers, you could have the outcome in either group. So that's 6 plus the 3, so that gives 14 parameters. And then we think about how many counts do we have that are independent. So we have the 3 treatments and 2 binary outcomes for each. So that's 6 in each group, but it's got to sum to 1. And so you subtract 1 and then times 2 for 2 groups. So that gives you 10 independent counts. So I played around with this trying to think of some clever assumptions that are reasonable. I could never come up with anything that would be very reasonable to make it identifiable. So usually using the usual assumptions, it's just not identifiable. Now there's one way around this that I came up with, and I'll just show it to you now. This is a paper I wrote with Konstantin Frangakis and Baker and Lindeman. And the idea was, instead of having 2 treatments, 2 randomization groups, what if we had 3 randomization groups? And this was a proposed design for the effect of walking on the rate of C-section. So we had T0, no walking, T1, walk 1 to 2 hours, T2, walk at least 3 hours. And then we had to come up with reasonable assumptions. And we thought we had 3 reasonable extensions of monotonicity that could make it identifiable. And that was that only T0 in group 0, which is some empirical evidence. Anyone assigned no walking would not walk. Something with consistent preferences, if they're assigned to walk at least 2 hours in group 2, they would walk, and they only walk 1 to 2 hours, they would walk 1 to 2 hours in group 1. And then just by design, if they're assigned to T2 in group 2, they would get T1 in group 1. And with these reasonable extensions, then we could have identifiability.
Yeah, it's clearly much more complicated in the partial compliance situation, but you were able to find a solution in this particular.
Yeah, only by having a 3rd treatment group.
Right, right. How would missing data come into play in either the randomized situation or the paired availability situation? Missing data is very common in biomedical studies,
Right.
whether it's for confounders or for outcomes. So how would that come into play?
Right. Well, I thought that might be a question too. So I have a slide and discussing some papers that deal with the missing data. Again, like what I was just talking about before, we have to add extra complexity, but it's all reasonable assumptions. And so there's two new assumptions, and again, very technical sounding names in the literature. One is latent ignorability, and that says that missing or censoring depends on group, which is what you usually assume, and also depends on latent class, and it's ignorability because it doesn't depend on outcome. But the new wrinkle is that it can depend on your latent class. And then there's something that's called compound exclusion restriction. So remember I talked about the exclusion restriction with outcomes, but then you could apply it to missing data mechanisms or to the censoring mechanism. And then here are some examples where these methods were used. One was a study of breast cancer screening where it was a survival study, and some persons refused screening and you had censored data. Another was a study of a mailing or a course to teach breast self-exam skills, and then there was a questionnaire to see how well they learned it, and some people didn't turn in their questionnaire. And another example was a proposed analysis of a study of placebo and finasteride, and the outcome was prostate cancer on biopsy, and some persons were missing biopsy. These are very complicated. We don't have that simple formula that I gave you before. It doesn't apply. You have to write out the full likelihood and get the maximum likelihood estimates.
So in the real world where we have missing data, sometimes we use methods like multiple imputation to replace missing data and proceed with the analysis on several imputed data sets and average to see what the effect is that we're going to report. Do you do something like that here, or are these assumptions that you're making that let you just use the regular complier effect that you've estimated even without imputing data?
Well, there's two basic ways to deal with, principal ways to deal with missing data. One is the likelihood method, one is multiple imputation. Everything I talk about here is the likelihood method because it's built into the likelihood. All the derivations, I didn't mention it in my talk, but there's simple estimates where the maximum likelihood estimates, as long as you were on the boundary of the parameter space. So this is you write this likelihood. The likelihood includes missing data. It includes the latent classes, and there's like it's conceptually simple but computationally difficult because you have to maximize the complicated likelihood. But you get the estimates, have reasonable precision, not ignorable maximum likelihoods with not ignorable missingness. And they are not ignorable, but it's not ignorable because of the missing depend on the unobserved treatment. So it's easier to maximize the likelihood, computationally possible, and I've never seen anyone try to use multiple imputation. I'm not sure how you would do it with this.
Okay. All right, thank you very much. Excellent presentation, good discussion with questions here. I'm going to turn things back to Marie.
Thank you, Dr. Marie, and thank you to everyone who participated in today's webinar. As I mentioned at the beginning of the webinar, we will be posting the slides and a recording of today's session on our website, prevention.nih.gov/mindthegap next week. You will receive an email with a link to the recording when it's available. Thank you.